Hello and welcome back to the Code Athlete. In this video I will tackle the qualification round 2022 from CodeJam, and I'm happy you joined me. I will upload this video directly after the competition. It will be quite a long one because I'm trying to tackle all 5 problems. So if you want to compare your solutions to mine, I always put in all my videos chapters, so skip through them to find your relevant part which you want to see, because I'm pretty sure you might not have the time to watch a 3-hour or 4-hour video on all the problems. And I'm putting myself a bit under a time constraint to practice already for Google CodeJam part 1 and 2, round 1 and 2, which will be under quite a heavy time constraint of I think 2.5 hours each, or 3. And that's why I will not explain every step I'm doing in much detail. I will probably talk quite a bit about my solutions during the solution finding phase, but I've seen in my last videos when I start talking about what I'm doing during the implementation phase, I'm getting pretty slow and hung up on the talking and not actually implementing very fast. So yeah, I think, well, if I'm pretty fast with these 5 problems, I think I'll make a run through in the end. And again, there will be chapters then where I will try to get the essence of each solution of each problem in the end. But if the video will be too long, I will think I won't do that. I hope you participated at this point, because yeah, you see this video when the competition is already over. I hope you managed to get the 30 points needed to get qualified for round 1 of Google CodeJam. And this video might help you to understand what problems were too difficult for you and why, how one could approach them, and what to better in round 1, which again will get much harder. A lot of people get quite disappointed by this, but this is very normal. Like in qualification round, basically everyone can succeed, because 30 points means just solving the first 2 or 3 problems, which are usually quite easy. And in round 1, only 4,000 people or 4,000, 5,000 people in the whole world will go through to round 2. So there's like a cut down of a lot of people. So if you don't manage it, didn't manage it in round 1, also in the past years, it's just important to keep practicing, keep participating every year. And I think if you're really into it, if you really keep practicing, you really have a good chance of succeeding round 1 in maybe already 3 years, 4 years, 5 years. Depends on your skill set, of course. And then you really have also an achievement. You really feel it because, yeah, like I said, it takes a lot of effort to get there. Not a lot of people manage it. So if you do, after those 3, 4, 5 years participating in CodeJam, you can be really proud of yourself. Yeah, so I just wanted to show you how I use my CodeJam template in this video also. You see here I've already opened my editor and I actually already created a qualification folder, but there are not my templates inside. So here's my CodeJam template folder, and I call the create folders function. I specify the destination directory, which is examples 2022 qualification. That's the directory I already created, but for this command you don't even have to create it. We'll create all the subpaths itself. And then I specify the names of the problem folders. I know there will be 5 problems in the qualification round, so I go just from A to E. And it creates this for me. And now I can go into my folder here. And you can see in the editor already I have my template folders. Just have a look at the main CPP. Yes, it opens nicely. And here I can put the result and the samples from task to check offline my solution. So I think that's about it. We can start. Here you see the problems. The first three are punched cards, 3D printing, and D1 million. Then there's chain reactions, and the hardest is twisty little passages. And you can actually see, I think there are not that many people who have already achieved a perfect score of 100. Yeah, so there are only 118 people got a score of 118. And the competition is already running for like 11 hours or so all over the globe. So yeah, this already indicates to me that it might be pretty hard to get actually a full score in this year, and maybe I'll stop after problem 4. We'll see how it goes. Yeah, because I'm about to start, I will just note down my starting time so I can in the end compute how much time it took me to get like a specific score, and then I can see how I ranked in the competition. So let's put this here in the corner, start, and then I can compute the time. And the start is now 12:05 p.m. of course. Snowing, by the way. Really the first snow this year here in Germany. We had a little bit of snow in January, but it's really nice now. Let's dive into this. Punched cards. And I will not be reading the task out loud as I do in my tutorial videos, just to be faster. Yes. Okay, so we have to produce some ASCII art, and the parameters are quite easy. I'm thinking about I think this could be a lot easier actually in Python, so I'm thinking about using my Python code. I will actually do this, yes. Which is not well prepared, I must admit. Let's hope it somehow works. Haven't used it in a long time. So yes, parameters are R and C. It's now annoying me when I type anything. So sorry I had to cut that out. Just put a symlink to my virtual environment so that the editor is not freaking out every time here I type something. So yes, so we read the input RC. It's one of my template functions. It's not defined. So it's really a bit broken. So we need to produce the plus strings and the dot strings. So there are kind of two types of strings, but then really in the first two rows we need to have something special. So the plus string, I will call it, is plus minus times 4 times the columns plus a final plus sign for the final corner, and the dot string is vertical dot again times C plus a final vertical line. Then the result will be a first new line because we start under the case $1, and then we can add 2 dots plus the plus string, but missing the first 2 characters because they get replaced by the 2 dots, and plus a new line again. The same happens then with the dot string, and then we have R minus 1 rows to go, for which we will just add a plus string and the dot string. And finally we just need again a plus string. Yeah. Size not used, so I can put an underscore here. RNC, I don't know, I think it doesn't manage to get the global keyword here. It's kind of weird. Oh, I haven't specified any tests, I should copy them over. And we have no module named SciPy, even though I just specified to activate the virtual environment. Now we have it. So there's something broken. It seems there's a new line too much in the end. I think it's this one here. Because that new line is produced automatically. Now we have exactly the right results. Actually I need to upload this solution upload here, which gets auto-generated, and I need to specify Python. Where is it? 3.7, not sure. I think I'm using 3.6 here. We updated that as well. Yeah, we got the points. Okay, let's move on. This was a bit terrible. I need to apologize for this. But actually deactivate this because I don't think I will need this again, hopefully. Hopefully I can stick to C++ now. With problem B. So again, this is quite an easy problem, I would say. Let's read those values in. Clear that array, then we can actually resize. We have 3 cartridges, was it? Yes. And each of those has 4 colors. And we can just go over printers and over the colors. Just check here that taken that correctly, and actually we have a default value mode because we need to print impossible if it's impossible, and let's say result should be a vector of numbers, and if the vector is empty then we say okay, we want to print impossible. So we will clear result. And now we can check what is the most of each color that we can use. So we will take the maximum at the minimum across all cartridges. I'll call this mini. We have 4 for each color, 1 mini. And we initialize this with 0. We go with 3 printers. Now we want to initialize this with a large number. And because we only need 10 to the power of 6, let's do it like this. Sorry, minis is just over the colors. And here we take the ink at that position with the current minis we have. Have a look at the minis. And now we can check if the sum of the minis is large enough. If total smaller this means we have not enough color, which we can just return because we cleared the result. It says size null and our default value trigger will print impossible for this case. Otherwise, we can initialize result with 4 zeros. We have the rest value of ink we need. Now we go through the 4 color channels. Per ink is equal to maximum of rest or the current minis value we have. Then we put this into our result and subtract from rest the current ink. So then the rest is decreased, and as soon as we are at 0 here, we will never draw any additional ink and we have our correct value. So this should work. Again, I need to use the test cases here, but because there are of course multiple solutions, they probably will show up wrong, but I will fix the test cases if mine are also valid. So the first sample, let's check the minis first. The ink should have been read correctly. Yes, this looks good. The minis is here 300,000, here 200,000, 300,000, 200,000, 200, 300, 200, and because I'm realizing the sum of the minis is exactly, so here the sum is of course different than here. This is, oh, I should have taken the minimum at this point here, right? Yeah, sorry, maximum is of course wrong. Yeah, because test case 1 has exactly one solution, I have to take the maximum basically in every channel, because this is exactly 1 to the power of 6. Here the minis is just not enough, so the volt value is triggered and reprint impossible, which is also correct. And then here Let's see if the minis were correct at this point. 6, 9, yes. 1, 4, yes. 1, 7, yes. 7, 1, yes. That looks all good. I will always take the maximum until I don't need anymore. And they have used a different distribution, but yeah. I think both should be fine here. Put it back to C++. And then we have a solution here. Let's go on. D stands for dice here. How many? You can have at most 10 to the power of 5 dice, and the dice can have at most 10 to the power of 6 numbers. Yeah, that's right. Good. So what I'm thinking here is, so this is problem C. If I can build a straight which starts at x equal 3 with a specific length. Let's say I have an optimal length straight and it starts at 3 and maybe goes up to, I don't know, 9. Then I have dice. Then I have here a die which has the 9. Then I have here a die which has an 8 and so on. But that means I could also have straight of the same length where I've decreased all the numbers by 1. Or let's say even 2, because then I get to x equal 1 here in the end. Because the die which has the 3 has also a 1. The die which has a 4 has also a 2. The die which has a 5 has also a 3, and so on. And the die which has a 9 has also a 7. That means I can assume that my straights always start at 1. Yes, maybe I shouldn't have erased this. And then really I have to, it's basically I think a cumulative sum thing. So because I start at 1 now, I can say if I want to have a specific length of road straight going up to L, then I need L dice which are greater or equal to 1. Every die fulfills this, of course. I need L minus 1 die which are greater or equal to 2. So yeah, this count greater or equal to 2. I don't know, I have not a good notation for this. And I need to have, so this goes on, and I need to have one die with a value of greater or equal to L. This is my condition to get the straight of length L. So I can compute these numbers here, how many die I have which are greater or equal to 1, greater or equal to 2. So this is basically, the maximum length is anyway n, so the maximum length is at most 10 to the power of 5. So I only have to check up till then. And yes, then I just go through this array, I think, again, looking at all the numbers and adjusting my maximum L to the smallest one based on these expressions here. So let's do that. What's the notation here again? Not sure if there's I thought this would be possible actually. It says that this is a double. This. E5 does not work. So here we have the counts, how many of there are, and we clip it basically because we don't need up to 10 to the power of 6. But now I want to have the numbers that are greater or equal, so it's basically a cumulative sum. But in the reverse order actually. So I will do this by hand. And we only need to update the first -1s, yes. We start at -2 already. This will get an update, and the update will be in this form. Yes. So now the counts has the cumulative sum. We can have a look at this. We can also have a look at this up here. And result we can put now to the maximum length, which will be n. And now we iterate again over our counts. So what was the relation we had that we must have at least L minus 1 counts bigger or equal to 2, so L minus 1 needs to be smaller than counts bigger than 2, or in general L minus I must be smaller or equal to counts of bigger or equal to I plus 1. So this is a formula, and here our result is of course L. So result is equal to minimum of result or the current counts for equals 0, for example. Yes, so it's just this. Yeah, that should be it. Let's see what we get. A lot of printing because I initialized the counts already to be this large. Could have actually just used n here as well. Actually, let's do this. Yeah. So here we have 0, 0, 0, 3 of the value 4. Yes. 1 of the value 6. Yes. 1 of the value 7. No, 5 and 6, 1, and then 3 of the value 7. Yes. 8, 9, and 2 of the values 10. And then this is the cumulative sum, which we constructed from the back, and we get at most 9. I think this should be right. So we already checked that 3D printing was the right solution, yes. So let's go for chain reactions. This is the example of top here, yes. And this can become quite big. 10 to the power of 5 modules with large fan factors. So I think we have to do some thinking here, but maybe a more complex graph is more suitable. So I'll maybe parse one of these more complicated samples. Case 3 we have 5 activators, and here we have 4 initiators. Let's draw both graphs. I need to understand the input reading, of course. First come the F values, and then the previous values. Okay, and 0 is abyss. So there is the 1 with a fun value of 3. Then we have 2, 3, 4, all pointing to that one. They have a fun value of 2, 1, and 4. This is actually the 4, and this is a 3, and this is a 2. Index, and then we have the 5th one, which points also into the abyss and has a fun factor of 5. It says the maximum is 14. I have 4 initiators, these 4 here. And it doesn't really matter because here I get this fun value, here I get this one, here I get this one, here I get this one, and from one of these I will also get this fun value. So it's basically all are once activated. So yeah, really I need to just, no, I always take the maximum, yeah, sorry. Not the sum, but the maximum. So one of these, if I would start 4 and this is still available, then I would take 4 and not the 3 and these 2. So I think the main message here is that from these 4, because they all go through this one, I can only use 3 values. Yes, because either I activate this and this was already used, because the first one I activate will use 2 but only get 1 value, yeah, and the other ones will get all the values. So the maximum I could make here is 9 plus the 5 is 14, and to get this 9 I would need to start with the 1 and taking 3 here. So this is some interesting observation, I would say, that we need to figure these groups out. Yeah, let's look at some other graphs maybe. So of course we are looking only at tree graphs here, that's obvious because we only have always pointing at one. Directed tree graphs, oh, they can actually be circles, right? Can be circles, interesting. But if we have circles, no one of those points into the abyss. The abyss, I don't know. Just need to look at some graphs here. So of course these two can be handled separately because they basically have no connection, and these two here can also be handled separately. So the abyss is really, yeah, always separates graphs. So we can handle the separated graphs independently. Then let's see, how many of those can we at most activate? If we would start here, so the only initiators actually are this one and this one, right? Those are the only 2 initiators in this graph. And here I have 3 initiators. If I would start with this one, I would go here around, and then I would use this one. Okay, so yeah, the number of values we can take is just the number of initiators we have, because for each initiator path we have exactly 1 value we take. So yes, so in the case where these, and we can't just say, okay, let's take from this graph the 2 largest numbers because they might be here and here. But as soon as one of those initiators is triggered, it will go around through both of them and can only take one of them, and then the other initiator will only take itself. So is it always best to just start with the initiator with the smallest value? Can we do this greedily? Because now in this case, for example, we have the two biggest here. We would want to start with the one which is smaller of these two, because then that one will eat up all those, and this one will take itself as value. Whereas if we would start with the bigger one, it might get self-activated if it's the largest, but otherwise we'll take one of those, and then the smaller one gets. So yeah, that's definitely worse. Is this in general the case? Because here it was also activating the smaller one was the best. Let's make this more complicated, this example actually, by putting some non-circular things in here. And then we have here initiator, here, here. Now we have 4 initiators. And maybe let's look only at this one with non-circular relations down here. In this graph we have 3 initiators, so we want to take the 3 maximums. This is a maximum and this is a maximum. And those can't be taken both, because if we activate this one will always be activated. That's the same here, so that's the reason why we can't take both. We will only take one of those. Why is this not the case for this one though? Because yeah, if we take this one might be already taken from this path. So here's not this direct relation where I can say if we take this one can't be taken, because actually this could have been taken from this initiator. In the optimal starting order. I'm really thinking that the greedy approach should work, but I can't express why. Really hard to see if that's true. Let's say we have an optimal order in which we activate those. Then the question is this number one of the 3 fun factors we add or not? If it's not, the problem basically reduces to splitting this graph into the 2 subcomponents. This one here and this one here. And if it's taken, then it means one of these subcomponents needs to sacrifice basically one of the initiators to take this value and doesn't take anything else here. So I think what I'm saying is divide and conquer could work, because now if I compute these 2 subgraphs, I can say, okay, if I only look at this one, I might want to select this one here if I activate this initiator, yes? If I only look at this one, I can't take both. but why did I do this pink? This should be red. I take this one and from this activation maybe, and then I take this one from this activation. And now I can merge those by looking at this node and see, well, this value might be, for example, bigger than this one. Then I actually want to trade taking this one for this one. But from these three values, I want to take the smallest away and trade it for this one. In case this is smaller than all these three values, I'm already fine. Then this one basically is not taken at any point. But if this is bigger than one of these three, I need to figure out how I can trade. So if this one is bigger than this one, it's easy. I just activate this first. And it takes this one instead of this one because of the maximum function. If this one is bigger than this one, it's also easy. I trigger this one and it will go through this one, but also through this one and take this one. And if this is only bigger than this one here, then it can't be done, yes, and that makes it somehow complicated. Do I always need to look at the first thing that's coming up, wandering back, and this one is the first, and I can't never get this one to work then? I think so. So in this tree-like structure, I can process the nodes from the endings. Then always go one node up and check if it's possibly bigger than the leaves, and then trade for one of those. Does this work in the circle though? I would start working from the leaves. The circles really make it a bit harder for this approach to work. But there can be circles, right? Yeah, it was not. It was specifically noted that no, add one module with the lower index, so we have not circles. Yes. Was it actually specified here? Yes. So we can't have circles. That's very good. That's very good. So I think this is a solution now I've described. Yeah, let's try to implement this. D. So the first node also always has to point at an abyss, right? Yes. So we can do a recursive call starting from the 0 node, and we need the backward links as well. Yeah, backwards. It's okay. And we have dictionary from each node pointing forward to one other node. And the fun values, yeah, we need the fun values. And we need n. Actually, we can store the forwards also. Let's actually call them PI. Problem statement. Now I want to construct the backwards. And we'll do this online here. Yes. Now we have the index shift problem. So they take the indexes 1 to n. Yeah, let's actually decrease those. So the abyss is now at -1, not 0. Oh, sorry. And is I correct here? Yes, now I is correct here. I will have a look at those. What kind of result do we need? Long, yes, just the sum of the fun. The sum of the fun. This is really a lot of fun. So what we need to return for a subgroup is the lowest node, which will be replaced by the upper one potentially, and the sum of all the stuff we have in here. So if we have all the sum, but we're going to replace this one with this one, then we update the sum by the delta basically between the two. So we will write a function that will return a pair of two integers. Recursive fun, let's call it, and we will look at a node. Yes. And the resulting function will be to compute this for -1, the abyss, because then we branch out into all the leaves. And I will say that the first value of this pair is actually we can directly take this as first. So all the logic happens here. And we need to go through all the parents basically, which is the backwards array we can use. Yeah, I think this should be quite easy. I hope this has no logic error, this solution. Feels kind of greedy and I'm not sure if it's optimal. I have not really proven it rigorously. Backwards of node. The current parent is backwards of node I. Yes. Yes, we will collect the sum and we will smallest close root. What are the fun factors actually here? 10 to the power of 9. I think, yeah, let's take it. I'm not sure. Have I initialized it to an integer or a floating point? Oh, to an integer. Yeah. So yeah, we take the recursive call of the parent and we add to our total sum the current sum of the subgroup, first entry, and the smallest close to root, because we always want to track the smallest, which we can then possibly to create the largest delta to increase our fun. And this is of course then the minimum of our current smallest close root and the thing we got back here. Second. And now if our current node value is smaller, if the fun value of our current node is bigger than smallest close root, then we add to the sum this delta, and we return the sum, and of course now the node itself is the smallest current node we can replace. In the other case, we can just return the sum, because we don't take the node at which we actually look right now. and so make pair sum, and the smallest closed root is still the one available to us, which we could potentially replace by the better parent. And I think this should be it. I'm pretty happy if this works. Yes, I think. No, it does not work. Sadly. Let's have a look at the PIs maybe at first. Yeah. So in this example, 1 points at the abyss. Yeah. 2 points at 0. 3 points at 0. That's right. And 4 points at 1. That's correct. And the backwards pass, it's not well formatted. Ah, yes, it is. -1 points to 0. Then 0 points back to 1 and 2. And 1 points back to 3. So that's all good, I think. Oh, I need to handle the case where there are no parents, because then I have the sum of 0 and yeah, so I need to handle the case if not backwards not count size. Okay, like this. If there's nowhere up to go, then this is an initiator and we just return the fun of the node as the sum and also as the one we can replace. And we get everything except for test case 2. So maybe we have to learn something about test case 2, which our algorithm doesn't get. And it's actually the one I've drawn here, right? We compute 60. Yeah, 60 sounds very wrong, right? -1 points to 0 and 4. 0 points to 1 to 3. That's correct. We're reading the FI values wrong. Let's maybe just check that, because I don't even know how I'm multiplying them at some point. So this node was an initiator in this case. In this case, we have date, and in this case we have passed through. So let's see what we get. For node -1, oh yeah, maybe we should put actually print statements directly for the returns. So node 5, oh yes, here. Node 1. It's in our setup node 2, of course, it's an initiator, yes. Node 2 is node 3, which is an initiator, yes. Node 3 is node 4 in our setup, which is an initiator, and node 0 is node 1 here. And it updates, and it results in a 9, and the 3 is the one to replace. That looks actually right. Node 4 is an initiator, yes. Node -1 is update. For node -1, yeah, the -1 makes this broken, right? If node bigger equal to 0, so we're not at the abyss, then we get the right solution. Yay! Was this correct? Yes. Let's have directly a look at twisty little passages. So this, I think, is a very hard problem. Let's see. This is an interactive problem. I usually like those. So yeah, this looks good, and this should definitely be fast enough. I mean, I'm walking through every node once. And here this backwards loop will only activate a total, so once for each node, and the sum of these sizes is exactly the number of paths you have, and those are exactly 1 for each node, for each module. So this is in the order of n over all recursive calls. And the recursive calls are of the order of n, and n was, I think, 10 to the power 5 or so. Yeah, 10 to the power 5, so this is fast enough. 10 seconds is not a lot, but yeah, this is definitely fast enough. I'm very happy with this. Nice. But for the interactive problem, we have to do some theory. This is a very interesting one. So we are basically blindly walking through a labyrinth. What's the English word for this? We have to estimate the number of edges. Do we get the number of rooms there are? So what is the input? Maybe let's have a look. Number of rooms and the number of operations. So I know the number of rooms because I need to know that to also be able to teleport between the rooms, because I probably have to specify that by a number. And I can see always how many passages there connect. And V means walk. TS means teleport to room S. E means you want to finish exploring and estimate that the cave contains E passages. Yes. So pretty straightforward interactive protocol, but no idea. I mean, we have, what kind of graphs could we have? Let's draw a simple one. Connect some of those. I think this is not forbidden. It doesn't need to be a planar graph, does it? Okay, let's keep it like this. Does it have to be planar? No, I think they can go over and under because we're in a cave. Each room has at least one passage. Yes, I've done that. No passage goes from a room to itself. This would be like small loops, and no two rooms are connected by more than one passage. So what we definitely can do is just teleport into each room and count the number of passages we see, because we see then each passage twice. One from this passage, for example, we see once here and once here. And this passage we see once here and once here. So if we can teleport in every room, count the passages, sum them up, divide them by 2, and we have the exact number. But I suspect that the K will be much lower. The K is always 8,000. We have just one test case, yeah. Well, I mean 8,000 out of n. So what is K over n? This might be a ratio which we need. It's 8 over 100. So 8%. We can explore 8% of the rooms. This might be not enough to have an error of 30%, plus minus 30%. So that approach won't work. Now I'm thinking, what does it help me to go from one room to another and know those numbers? Yeah, okay, I mean, sure, if I have if I start at one room and always walk randomly, so let's say I start here, walk randomly, that means I end up here. Now I walk randomly to one of those 4. I walk here, and one of these 4. What I'm trying to say is I have the feeling if I walk quite a bit, I'm very likely to end up fast in a room which has a lot of edges. Whereas it's quite unlikely to end up in this room because I need to go from this room exactly this one edge. There are not possible ways to get there. actually put in here the number of edges. 2, 3, 4, this is actually a 5. 3, 2, 1, 4. So I assume you would somehow end up more often in these, in the middle here, than these edge things. And it's not that bad to miss actually this room and then this edge or so if we need to find the rooms with a lot of passages. So it's really maybe a good thing to walk through a few passages to see when we end up in a room that has a lot of them. This is a really strange problem, I must say. Do we have some limit on P maybe? Each room has at least one passage connected to it. So in this example, I say we have 8% of operations we can do on a large graph. I mean, you can easily handle the cases where n is smaller than k. Like I already said, we teleport just into each room and then take half of that. Five threes already. I have here 1, 2, 3, 4, 5, 6, 7, 8. 8% of those would be just maybe a k of 1 or 2. But I think it doesn't scale that way, so say if we have a k of 3. Now what I'm also thinking is if I maybe are in this room and I walk one passage into a room with another lot of edges, so I walk here maybe, and I know I've seen here 4 different passages. I walked 1, and here I see again, next to this one, I see 3 more passages. And I know that these 3 and these 4 can't be the same, because otherwise there would be another passage between the 2 rooms I just traveled. So now, by adding this number and this number, and subtracting the 1 for not counting this x double, I have already a minimum number just of the edges that connect to these 2 rooms. Or actually, I have an exact number of edges connecting to these 2 rooms. Same goes for a triangle. If I at one point know that there's an edge between these 2 rooms, and I know there's an edge between these 2 rooms, I can conclude that this 4 here, I'm counting here these 2 doubles, so basically I'm not counting those, but again I get 2 more. So now I'm thinking, what if I just start in one room, walk one passage, do this estimation for these 2, and note that there's an edge between those 2. and then I teleport into another room and walk again one passage. And I can somehow, for example, if I start here, walk here, I get the counts, and I teleport here and I walk here, then I don't know that these are connected, but maybe now, because I have this connection, I can basically do all the counts, and I have double counted this one, and I can maybe compute a probability based on all the counts that there was an edge here, and subtract that probability from my estimate. I'm thinking about basically for every edge computing a probability and adding those up in the end and updating those with the information I get. But I can't have a square matrix. But I can have a square matrix over 8,000. 60 million. Because the other nodes will always be symmetrical, basically, the ones I haven't visited. I will try to implement something like this. Not sure about details, but let's see. So this is an interactive problem. Let's see what the error code is. Yeah, so the IA error code is -1. So read input for each test case is NK. We want to use this function because it's called just in, I think. I hope this works. Just let me look this up. Yeah, I can just call in, get the value, just to make sure that I'm catching the -1 in case it comes somewhere. N and K, we've got that now. And then it's always of the form I do an observation. I wanted to calculate, initialize the matrix, right? Top matrix. And because my first row doesn't correspond to the first room, but to some random room I start in, I will have an index order vector, yes, which I will clear. And I also need a backward sorting, I guess, of the form reverse index order. And this will have the resize of k plus 1, because I have k rooms explored plus the one other group basically. And I initialize it with all ones. Prop matrix. Yeah, let's deal with the floating points. And again, it's a k plus 1 times k plus 1 matrix. Do we initialize it with something? I would say with 0, right? I'm still not really sure about the strategy, I must say. Also updating this probability matrix is gonna be really bad. I don't want to do that. I think I really just want to record the hard facts, which will be the connections. Which I will save in a dictionary, I guess. and the number of passages I explored in each room. And again, the connections will be cleared, and the PE I will initialize to n, and with all -1s means one unexplored. Now, in this phase, I can directly process this answer by saying, okay, in room E, I know the passage is PI. Let's handle the case where k is bigger than n, because I think we should manage to get those exact. K greater or equal to n. Can even handle n plus 1, because we can do k operations. We start in a room, and after we get information, so we have k plus 1 informations, I think. And I of Ri equal -1. We could have initialized with zeros because they all have at least one passage. Continue. In the other case, we want to teleport. So teleport, and I want to teleport into room I. I think they are indices from 1 to n, so of course. Have PI doubled here. And after we have explored all the rooms, we can just sum it up. E was for estimate, yes. Total divided by 2. This needs to go all here. And then we can return the calculation function actually. And I want to test if we have this test case actually in the data set. So we download now the tool. We have the local testing tool. Does my execute script work with this? Starts directly with a big test case. See already here a lot of passages. Get a timeout here. We need to get an answer for this one. Number of tokens expected, 2 found 1. Says the judge. Because the output wasn't printed in one line. Why is that? Those are all these maximum test cases. I'm pretty irritated by this. Yeah, so I don't know, maybe these cases don't even exist and this was a waste of time. I will actually have a look if I can Judge is not running on its own. Now I've broken it. Just change it on. So somewhere it actually uses that n is bigger than k? Or what? So I'm not exactly sure where this is. Yeah, I don't understand this actually. Can I make k bigger? Because for 8002 it worked. Now here my program should actually needs to be bigger than n-1, right? Yes. Can I actually specify that my com type is a string now? Or is it automatically taking care of this? Seems so. Thought I would use this in the. Oh, my in values are actually integers, so that's fine. Yes. Did I get the first test case right? I got 50 cases correct? What? That seems very random. Where's the communication where I get actually this large sum from? Is it? Here happened something. But for some reason the read input function is not working properly. Why is resize not filling it with -1s? Okay. I'm a bit irritated. This needs to be done. But now we should get all the test cases right in this case. Still not helpful to actually solve. How much time do we actually have for this? Is there a time limit? 20 seconds for all the interactions, yes. I reduce the number of test cases. Yeah, I now get exact answers, so that works at least. Okay, let's get back to the old test cases and find something that can handle this. Still no idea how. Am I just randomly visiting and taking the averages of those? I mean, let's try it. I have no better idea actually. So here we select a room which we haven't observed yet. Then we will just observe that room, I guess. Note the result. And in the end, count plus plus, sum plus equal to P of I. And then we have an estimate of value of sum divided by counts times n divided by 2.0. Again, this 2 is from this 2 basically, counting all them double, And this operation basically says, okay, sum divided by counts visited. Count should be k plus 1, I think. We get an estimate of the average passages per node. We scale this up to the number of nodes we have. And see if that estimate is somewhat usable. I don't know. What did I do wrong? Did I have used count somewhere? I have not. What is the problem? I think I cannot cast. That's what's confusing. I want to cast the sum, and then everything else should be flow. Oh. Yeah. I got actually 10 cases correct. That is surprising to me. Okay, let's scale this up to all the test cases. It says too few correct answers because we need 19. I'm surprised that this should really work. I will actually submit this because I'm not sure if I have any good ideas. Yes, except for maybe traversing and finding rooms with more nodes even. Because exploring just 8% of the whole cave means I can have bad luck and find only rooms with very little wrong answers. I got 100 test cases correct. turn this off, I think. It tries to explore multiple. And I will turn off the interactive conlog. Really gets all of them correct. That's strange to me. Seems that test case is correct. So I suspect this averaging is already quite good. Therefore, I'm thinking about implementing this walking and just ensuring that, because I'm probably underestimating. I think I'm underestimating because, yeah, or I'm overestimating actually. What doesn't happen easier, if I underestimate or I overestimate? Overestimating would mean in the 8% of nodes that I visit, I would get a very large average of nodes, which is not consistent over all points. Meaning not consistent over all points, meaning I would need to find more of the low count points. But if I take passages, it seems to me that I'm more likely to end up in nodes that have a lot compared to nodes that have only a few passages. So that will only bias me to higher numbers, not lower ones. Well, now I have a quite different idea here. If we mark this as problem. Let's draw an interesting graph or something. It has maybe like a central node. If I start somewhere and take one passage, what is the probability to end up in this node? Here it's 100%, 100%, 100%, 50%, 0. 0 if I start here and take a passage. We could exclude that because we know numbers. 50 and 50. If they connect with this. Those have all 3, but this one has 6. Now here again I can explain the problem with the averaging. If I have bad luck, let's say, and I visit 10% of the points, I have here even only 8 points, so even 1 point visiting would be more information than we have for the 100,000 and the 8,000 K. So just visiting 1 point and taking so here I would estimate an average of 1, here I would estimate an average of 2, 2, 2, 6, 3, 3, 3. The 3 might be the most middle ones here. I don't know. Or maybe the 2 is more middle. But we have quite a chance to miss those. I'm wondering if I should try to just iterate here, because I'm going from 0 to K basically, and maybe the rooms are structured and I should just randomly sample integers. Oh, at this point. Yeah, let's do this. I will just try this because I'm... If you look at the random integer inside a range function for C++. Some random integer function. Okay, I found here something. Let's try this. Random device ID. And this is the Mersenne Twisty random number generator. Then I have a uniform integer distribution. It's minimum is 0, maximum is, I think, n, right? Yes. That's exclusive. Okay. How to use it? What about that? Yes. So here you can say uni of uniform is random number generator, and here I will just take a new random number till we found a room that's not explored yet. Let's see if this still works here. So the maximum must be exclusive. Let's see what happens. I have no idea. Would be really strange if that would be making the difference between working and not working. Yeah, okay, it's not working. It's still so strange that we have 100 test case correct here. I think that means they are specially constructed here in this test case. Now from the operations I can use teleporting and walking. And the teleporting I'm using quite a bit. The walking really, I think, produces higher probabilities to just get into a room with a larger number of edges. So it biases me. But if I can account for this bias, it might actually work. I just don't know how I can account for this bias. if I am blind to this graph structure and I am at a node and there are like two passages, yeah, then of course I will end up 50-50 in this node or in this node. And after I end up, I can count the edges going in here. Can I, from that observation, assume that this one might have the same number of edges? I don't think so. Like we could have clearly this structure, like a flower structure, where we have a lot of these nodes here, which have two passages, one going to one with a central, which has a lot of edges, and one going into somewhere which has almost no edges. So it's more about the observation starting somewhere, going somewhere, starting somewhere, going somewhere, and then maybe again I'm starting somewhere and going again here. That tells me that this might have quite a lot edges compared to anything else. Let's think about this operation starting at one point randomly and walking one passage randomly relative to this point. What are the probabilities of walking these specific edges? There are 1, 2, 3, 4, 5, 6, 7, 8 points. So this one would have the probability of 1/8 times 50% plus 1/8 times 50%. So this would have the probability of 1/8. This edge here would have 1/8 times 50% plus 1/8 divided by 6. So this would be more like 2/3 times 1/8, so 1/12, I think. And this is symmetric, would be also 1/12. That's already unexpected, so this one here, for example, would have 1/8 plus 1/8 times 50%. 16, so this is 3/16. That's even larger than this one. These will have the lowest, I guess. This one has the same probability as this one because this is a 2 and this is a 6. This one has 1/3 plus 1/6. 3/6 times. I think it's 1/16 just. This has 1/3, 1/3, 2/3, 1/12 again. And this one is symmetric, and this one is symmetric, so it's also 1/12, and this is 1/16. So I get with higher probability actually the edges which are not connected to high nodes. That is already quite interesting. Still, I'm feeling I haven't done anything smart yet, because I need to take into account the observations I have at my start point and my end point. So let's say, what is the chance of trying to actually replicate this graph? I think it is quite interesting. And what are the chances of observing a specific node by this operation of starting randomly somewhere, walking randomly somewhere? And then by observing, we count also these here. So when is this observed? It's observed when I start here, or I start here and walk somewhere, or I start here and take one of these two paths. So this is observed in 2/8 cases plus 1/8 times 2 out of 6. Okay, this is observed when I start here or here, so it's always 2/8 plus the probability to get one of these nodes from some other node, which in this case is only getting to this one from this one, which is 1/8 times 1/6. So here okay, what about this edge then? This is 2/8 plus 1/8. Oh, if I go start here, I get this also definitely, so another 1/8. If I start here, here, or here, I need to take one triple chance, so it's plus 3/8 times 1/3. Plus 1/8 times 1/5. So this has a pretty high chance to be observed actually, because it's connected to a node that has a lot of edges. That means it's likely that we visit this one. And that's true for all of these edges. So we really can, by this operation, I think, dramatically increase the observational probability of those edges. Thinking of implementing this search pattern, checking how many test cases I get correct, because it will probably be an underestimate now. And then multiply this by some factor to increase the number of test cases I get correct, and hope that it works here as well. It seems very sketchy. Can I can I specify maybe correctness ratio of not 1/3, but maybe smaller? So I could say here factor is equal to 3, and these two numbers are factor -1. This is factor, this is factor, and this is factor +1. And then I could probably increase this factor to reduce my correctness ratio. Then I could fine-tune my scaling factor for this operation. Now I'm wondering if it's important that I start randomly at some point, or can I subset my random start to points I haven't visited yet? Is that increasing my performance or decreasing my performance? I think I will test that just. I think we should first start like this. We only do half operations. Oops. We first take a walk and then choose a random room. Walking is just printing a V, right? Was it? Yes. Yes. So const of previous error gets inserted in R, and because it's bidirectional, we get like this as well. Now we want to jump to a random room. In the end, we always need to find a new room to jump to, possibly. Yeah, we can't update our connections here. Not sure if we need those anyway. Yeah, so if we have our connections, we can actually do... I'm wondering if I should subtract the connections from these counts and then add them in later on. And I think we should do this because I would now assume I would just now count them all once and divide them by 2. Put a scaling factor on that. But yes, basically, I can initialize the sum. Yeah. Con count. Let's call it double con count. Cons of I. Oh, actually, I need to check here because it's always r minus 1, right? So I should put 0 minus 1, 0 minus 1, 0 minus 1. And now the estimate would be just the sum, but in the sum we counted all the connections double, so we need to subtract them. But this count is also double. Let's see what we get here. Yeah, we get a lot of wrongs. Let's try some scaling. So we're probably lower, right? This is roughly 5 million. Factor of 6.4 I get here. And I will now sharpen the tool to make the acceptable range smaller. Again, this would be, I'm giving up, I think, after this, because this already feels like a super strange solution, and it looks like it works in quite a lot of cases. 94 cases correct. Let's just check the ones that got wrong. If it was too low or too high. So here we are too low. Quite a bit. Correct, 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 correct. What? Is there here nothing printed? Is this the line for that one? I think they get a bit intermingled. You're to correct something. This was even with our reduced interval, right? Again, too low. Are we most of the time too low? It's something I should have checked maybe. No, here we are actually higher. Here we are lower. Higher, higher. In the very small cases, we tend to be too low. In here as well. So I'm thinking of maybe putting the factor to 5 here and increasing this by, I don't know, let's find another wrong one and compute to the lower bound the ratio we needed. Another 1.2 higher times the 6.4 we have, 7.7. Let's see how many we get now. Oh, here actually, okay. Get a lot more wrongs now. But this is very close to the 1/5 border, I think. So maybe let's get back to the, go back to the 4. What's more important than actually getting it right is to have it stable. We have got 43 test cases correct, okay. Let's see about factor 4 again. Yeah, we'll upload this just to check. That works. No, it's still not. Maybe the 6.4 was better actually. I think we got more wrongs now. No, actually it's better. We just got 4 wrongs. And that's still not good enough for you twisty little passages. Why is that test case so different? I mean, testing with this is also not really super helpful because it seems to have quite a big deviation from the true test set. I mean, what I like about this right now is that this estimation factor, so like I said, we observe 8% of all points, right? Basically, our previous estimation factor was this one here, which is n100 divided by counts, which is 8,000. So 100,000 divided by 8,000 divided by 2. Oh, so our previous estimation factor was actually 6.25, and now we have 7.7, which is bigger. Is that worrying? Our previous estimation factor was only 6.25. I thought we would observe more edges by doing this walk. Wasn't it that we computed that the probability increased for observing? I mean, we miss half the operations now, right? That's really something we have to deal with. Is it informative to take longer walks before teleporting again? It's a really weak problem. Yeah, I promise to stop after this. I have no good idea here. So, yeah. I'm very interested in the analysis of this problem. So, let's just compute my scoreboard position if I would have participated in the night. It started at 12:05. And I think I got pretty fast the small problem. So this 1114 must correspond to, I think, 1214. So I need to basically add an hour to this final time. And I've got no penalties for all the other problems, right? No. Only here some attempts, but those penalties doesn't count if I don't submit this. I will only count my 71 points now. And then I finished at 12, we said, plus 1 hour, 13, 16. Did I really solve that so fast? I'm quite impressed from myself. So this would be in total just 1 hour and 11 minutes with the score of 71. Okay, so now there are already quite a few with 100 points. Here a lot with 40 minutes submission time. Yeah, 1 hour 11 would be currently somewhere around here, but of course the number of perfect scores will increase now, but then those might also have taken quite a lot of time for this problem. So I would be around top 300, I say, right now. But of course it's hard to really estimate at this point. Last year I managed to solve also the fifth problem, which was also quite hard. And this year's hardest problem, to be interactive, which is already unusual, it seems really strange that this is possible. In combination with that it seems that they've actively tried to come up with very difficult graphs to estimate. So that there's somehow a very robust method for all these different kinds of graphs is very interesting, at least. I will think about this today, of course, a bit, and if I come up with a solution, I'll probably record an additional video just for that, or maybe concatenate it to this video directly. But currently I have no good ideas at all how this could be managed. Deludes me. So yeah, I hoped you liked this video. You could compare some of your own approaches to mine. I said I would go through how much time did I spend on this one now? Almost 2 hours now on Twisty little passages. Okay. Still unsure that I calculated this correctly. Yeah, it seems so. I have to look at the video. I'm surprised that I was this fast. Very happy with that. And my username is broken. I should fix that probably. Okay, so yeah, let's do maybe a short run through the problems. I think this D1 million was still quite simple. Yes, it was very simple. I think I don't need to say anything about this. Maybe a bit more about the chain reactions and what I did there in the end. It was here, problem D. So basically, if I look at the node, to formulate it more clearly, if I look at the node, I have all its basically parent groups. And I can say, okay, let's say I have solved this parent group, assuming that this one would point into the abyss. I have solved this one and got the perfect initiator activation. And I would, for example, have in this case 2 numbers that were selected, and I report not only the sum of the fun values of these 2, but also the one that is going in here from bottom to top, basically the first one I approach. It might not be this one, it could actually be that both the initiators are actually the most fun values. Then I would report, like if I have multiple paths to get to multiple of these red cross values, I would take the smaller one, because that is the one I potentially want to I want to potentially substitute with this one to get the greatest delta and improve the fun by the most. And I do this for all the other basically subgroups, subparents here. And now basically what I'm telling here with not the sum but the smallest close to root value, it's telling me which one I should substitute with this one. If this one is bigger than any of these smallest closest to roots, basically I look for the minimum of all these subgroups for the smallest root. And if it's this one, I can say, okay, I activate it in such a way that this one should be traversed by this subparent group. That means this subparent group basically gets activated first. And one of the initiators is then walking through this one, taking this one, and that means all the other parents are then handled independently, and we already solved them optimally. So therefore we can compute the new sum we get for this and the new lowest minimal score basically is this one, because it's the only lowest score at this point that we take, because we can't reach the other ones anymore. But in the case basically where we had that the lowest one is this one, we can make sure that this one is taking now this one basically. This one was bigger, right? And this is the biggest difference improvement now, by making sure that inside this group, because we have never taken this one, actually we can, these 2 groups can be switched independently, activated independently, because it doesn't matter, it will always take the top leaves here. And we can say, because we want to replace this one, we say we actually activate this first, and then it walks through all of these and takes this one instead of this one. So we update our total sum by this difference. But this means now in future turns that we can't actually change the orders anymore between the subparents and also these nodes. And that's basically encoded again by having only this smallest value and determining thereby this path and this activation order, this going first, this going second, and this group going third. But yeah, for each node we can then say, okay, this is the optimal sub-solution for the subgraph. And why is the aggregation of this then still optimally? Well, because this node, we can really again say, let's say we have for this whole graph the optimal solution. Question is, isn't this optimal solution this one taken? If yes, so then it has to be taken by one of the subgroups here. And taking this path away, this will be the first path, by the way, which takes this, splits up the other parent in, again, some other groups. And these we need to solve optimally, of course, again. And by the construction, they are already optimally solved and didn't take any of these intermediate nodes, which need to be taken by this first path. And if this one is not taken, then in any way, these 2 nodes need to be solved independently and optimally. And by construction, we have done this. So yeah, that is kind of the proof why this chain reaction computation works. And it was a surprisingly simple code in the end, I must say. So the recursive function, I would say, was quite simple for this type of still quite complex problem to get your head around it. So I'm pretty pleased with that. Would be, of course, the cherry on top to have this tricky little passages solved, but I'm just astonished, and I think, again, CodeJam came up with some great problems here, still interesting after all these years taking part in this competition. And I'm really looking forward to what round 1 holds for us. Wish you all the best of luck for the upcoming rounds. If there's an intermediate kickstart round B, I'm not sure when it will be, if it's before round 1 or after round 1. I will try to either take part in that if it's on the daytime in Germany, or I will use those problems in the following weeks to do more tutorial-like videos with more in-depth explanation, and for myself to practice the upcoming rounds of CodeJam. So if you like this video, please leave a like and a subscribe. Really helps me out to just get more people motivated for this kind of problems and coding. I think it's a great fun. And if you've learned something, or if you have questions to the problems or my approaches, or maybe even how I came about to think of it like this, and maybe you want to share your story, what you started to think about the problems, then feel free to leave those in the comments. I will happily reply to every single one, because the channel is so small, I can still do that. And yeah, so I hope we can start to communicate about this, maybe grow a bit of a community, and challenge together the CodeJam round 1 and 2 and 3. So that's from me. And the solutions I will again upload, of course, to my GitHub repo. The links are in the description below. And on the end card you will find some videos to my Google CodeJam template, which I used, or the channel itself. So have a look at those. See ya!